Okay, today we're going to look at the potential energy stored in a spring. If we start off looking at a horizontal spring that's attached to some fixed barrier, so here's our spring. We'll put a little plate on it, and if this is in equilibrium, if we then come along and apply some force to the spring, that spring will then start to compress some distance x. But the more we push on it, the more it displaces. So there's a relationship here. If we look at a graph of the displacement versus the force, we see that as we keep pushing up and up and up, the harder the force, the greater the displacement. So we can see there that it's a variable force. So we can find the average force applied to it as some F starting point plus F at some final position divided by 2. Well, if we start from position 0 or equilibrium, then that's 0 plus this Fx over 2. And Hooke studied some of this and basically came up with Hooke's law that says that the compressed force in the spring is equal to kx. Let's write that a little bit better. Okay, where k is equal to a spring constant, and that spring constant is just an idea of how stiff the spring is, and that's in units of newtons per meter. So a large spring constant means it's a very stiff spring. A smaller number, then it's a more flexible string. And this x then is the displacement of the spring, and that's in meters. And you can see if you multiply k newtons per meter times a meter, you're left with just newtons to give you that force. So if the average force, then as we increase that, we can then get into where the the F average then, picking up from where we left off, is then going to be Fx, which would be, here, let's rewrite that just for completeness sake, Fx over 2, which then becomes 1/2 kx. So there's your average force. And we'll be able to relate this then to the potential energy. So 1/2 kx is this average force in a spring. Fx is the force to compress it to a point. So let's take a look at some formulas that we can develop out of this and make sure we have those concepts clear. Erase that and go over to the next slide. So formulas, we just said that Hooke's law is F is equal to kx, and the negative sign says the x and the force are going the opposite direction. K being the spring constant, x being the displacement. We can then take it to looking at the work done by the spring is a force times a distance. So if that force, again, here we have to look at the average force because it varies. So from before, we saw on the last slide, we saw that the average, let's put this average here, is then the 1/2 kx, and the displacement is also that x. So we end up with the work done as 1/2 kx squared, and that in turn becomes the potential energy stored in the spring. So here we have Hooke's law. And here is the potential energy stored in a spring. Let's take a look at an example. So here we have a 2 kilogram mass that's suspended from a vertical spring, originally in equilibrium, and the spring stretches 5 centimeters. So if we sketch what we've got, is here's condition 1, here's the spring, and it's in equilibrium. So here is going to be our neutral point. We then come along and put this mass on it, and the spring starts to stretch out. So here's our mass, and this is 2 kilograms. And let's just take our reference point to here. This stretches an x of 5 centimeters. So given that the mass is 2 kilograms and it's displaced 5 centimeters, and again we need to convert that to meters, so we divide by 100. So 5 centimeters, 100 centimeters in 1 meter gives us 0.05 meters. So now we have mass. So if we want to find what is the spring constant is F is equal to Kx. So K then, solving for K, we end up with F divided by X. So we have a force. The only force is we have a mass, but we don't have a force. But that force is gravity, force due to gravity. So we end up with really mass times gravity over that displacement, which is 2 kilograms times 9.8 meters per second squared, all divided by the displacement of 0.05. So if we put that into our calculator, we get, let's see if you can see that, 2 times 9.8 divided by 0.05 is 392. So we have a K of 392 newtons per meter. So that's our answer to part A. Now, can we find the potential energy stored in the spring as a result of that? So, part B, we're looking for the potential energy. I'm going to let you guys see if you come up with the potential energy in the spring, and we'll see what you guys come up with.